Welcome back to this introductory lecture on set theory. In the second segment, we will provide a couple more definitions. So let n be an arbitrary non-negative integer. If a set S contains exactly n elements, we say that, first of all, S is finite, and also that n is the cardinality of S. So the cardinality of a set is simply the number of elements in a set. And the way we denote the cardinality of a set is by placing the set between vertical bars. So remember, the important thing here is when you write this, even though you have a set in the expression, because it is surrounded by vertical bars, you're talking about the cardinality of the set, that is an integer, a non-negative integer, not a set. So this is not equal to a set, it's equal to the number of elements in a set. And again, if a set has a given number of elements, say n, then we say the set is finite. So for example, the cardinality of the set 1, A is 2 because the set contains two elements, namely 1 and A. The cardinality of the empty set, notice every set has a cardinality, or at least every finite set, and the cardinality of the empty set is 0 because it contains 0 element. In fact, the empty set is the only set that has cardinality 0, whereas I'm sure you can imagine a lot of sets with cardinality 2, say. Now, the set of natural integers is also a set, so it's perfectly fine to ask what is its cardinality. But what is the answer? Well, the answer is n does not have a cardinality because there are no non-negative integers that represent the number of elements in n. Since n contains an infinite number of elements, you can't count them. So we say that n is infinite, and in fact, every set that is not finite is said to be infinite. So an infinite set does not have a cardinality. Our next definition, and the last one in this segment, is the power set. The power set of a set S is the set of all the subsets of S. And the power set of S is denoted by the expression P of S. So you start with a set S, and you consider all of its subsets, not necessarily its proper subsets, but both the proper subsets and the subsets. You take all of those and you put them together into a set, and that set is called the power set of S. So all of the elements in this definition should be familiar to you by now, the concept of a set and a subset. But sometimes the concept of a power set gets a little bit tricky to use in practice, so let's look at some examples. Let's compute the power set of the set 1, 2. First of all, the power set is a set, so we start with the left curly brace, and then we're going to list the elements of the power set in some kind of logical order, even though the order doesn't matter, but for us to make sure we don't forget any of the subsets of 1, 2. So we're going to sort these elements from smallest to largest, that is the one with the smallest cardinality to the largest cardinality. What is the smallest subset of 1, 2? That's right, the empty set. Don't ever forget this one. The empty set is a subset of every set. So it goes into the power set. Now, since there's only one set whose cardinality is 0, let's move up to cardinality 1. In other words, the singleton sets. Which singleton sets, if any, are subsets of 1, 2? Well, the singleton set containing 1 and the singleton set containing 2. So there are two more elements in the power set here. Now, the next size up is cardinality 2. how many subsets of cardinality 2 can we find for the set 1, 2? Well, there's only one. It's the set itself, since it has two elements. So don't forget, the set 1, 2 is an element of its own power set, since 1, 2 is a subset of itself. And that concludes the power set of 1, 2, which has four elements, or four sets. So remember, the power set is a set, and it's a set that contains other sets, by definition. So what is the power set of the singleton set A? Let you think about this one for a while. Okay, so did you figure it out? Of course, the empty set is an element of that power set, as well as the whole set itself. And there are no other possible subsets of this set. So the power set of this singleton set has two elements. How about the power set of the empty set? Sometimes I write the empty set with the pair of empty braces like this. Sometimes I write it with this symbol, so you get used to both. So what is the smallest subset of the empty set? Well, you get it, the empty set itself. Are there any bigger subset of the empty set? And the answer is no, since the empty set has no element. You clearly can't find a subset of it with one element or two elements or more. So, in conclusion, the power set of the empty set is not the empty set. It's the set that contains the empty set. Make sure you think about this one and get comfortable with it. Now, as a last example, let's take the empty set and put the empty set inside of it. In other words, let's start with this power set that we just computed, and let's compute its power set. What do we get? Please pause the video and solve this problem. Okay, so let's see what you found out. Again, the empty set is a subset of this one, because the empty set is always a subset of any set. Now, what other subset of this set did you find? That's right, the set that contains the empty set, namely the whole set is, as always, a subset of itself. And these are the only two subsets of this set. Therefore, the power set contains two elements. Notice the similarity between this case and that case. In both cases, you're asking for the power set of a singleton, and the answer is always the empty set and the singleton set itself. Now, the last point I want to make for now about the power set has to do with its size, or its cardinality. Remember, the power set is a set, and if it's finite, then it has a cardinality. And I want you to focus on the examples that are on the slide right now and try to find a pattern to compute the size of the power set. Do you see any pattern emerging? One simple observation to get you started is that the bigger the set, the bigger the power set. That makes sense because if you start with a bigger set, it has more subsets than a smaller set. So notice, for example, this power set has the most elements, and the set we started with here was the biggest of these four examples. At the other end of the spectrum, this was the smaller power set, only had one element, and that happens for the smallest possible set, namely the empty set. So you see what I'm talking about? I want you to find a pattern. In fact, ideally, you should be able to come up with a formula. So let me get you started on this. Let's say we start with a set S whose cardinality is some integer n. So for example, here the cardinality of S is 0, the cardinality of S is 1, the cardinality of S is 2. What I'm asking you is to come up with a formula for the cardinality of the power set of S. So in other words, what's the cardinality of this power set, that power set, and that one? Please pause the video and try to come up with a formula by discovering the pattern. You don't have to prove the formula, you just have to see it and write it down. So one thing that could have helped you to find a pattern is to keep going and maybe compute the power set here for a set with not 0, 1, or 2 elements, but maybe 3. So if you haven't done that yet and you didn't come up with a formula, compute the power set of the set 1, 2, 3, and then come back and we'll discuss that. Okay, so I assume that if you don't have a pattern, at least you have all the necessary data. You notice, for example, that the size of this power set is 1, then 2, then 4, and then 8 if you computed the power set for a set with 3 elements. So what happens is that all of these cardinalities for the power sets are not only powers of 2, 1, 2, 4, 8, but notice every time you add an element to the original set, you multiply the cardinality of the power set by 2. So here you have 1 element, here you have twice as many, then you have twice as many, then you have twice as many. So in other words, it looks like the formula is going to be something like 2 to the power whatever the size of the set S is. So in conclusion, if the cardinality of the set S is an integer n, then the size or cardinality of its power set is going to be 2 to the power n. So in particular, what it means is if the original set is finite, then the power set, its power set is also finite. However, the size of the power set grows very fast in the size of the original set. Now, you don't need to be able to prove this formula right now, but later on in the course, we'll be able to prove it in maybe a couple of different ways. And this concludes our second segment on the basic terminology of set theory.